Good evening, all. Can we wait for 5 minutes? Let others also join. Good evening. Uh, Welcome to the live interaction section of week 2 of our course Computational Fluid Dynamics. So, in second week's videos, I hope you might have been gone through that. Here, a fluid developed flow through a triangular duct. That is, in first week we have discussed about rectangle duct in the uh, lecture videos, where it was comparatively easy to discretize the fluid flow region or fluid flow domain. But we know that CFD is nothing that related to very defined or rectangular regions. So to show you how other kind of domains, if it is not conforming to the rectangle coordinates, how the calculation can be done. To introduce that concept in second week, a fully developed flow through triangular duct has been discussed. Hope you might have gone through that. So let's start our uh, questions. So first question: with respect to figure 1, for the given coordinate system, the equation governing equation describing the steady laminar flow through a triangle duct is given by which of the following? Option A, mu into dou square u by dou x square plus dou square v by dou y square is equal to minus dp by dz. Option B, mu into dou square w by dou x square plus dou square w by dou y square is equal to minus dou p by dou x. Option C, mu into dou square u by dou y square plus dou square u by dou z square is equal to minus dp by dx. Option D, mu into dou square u by dou x square plus dou square u by dou y square is equal to minus dp by dx. You can inbox your answers. The question is, which of the following is the governing equation describing the steady laminar flow through the triangular duct as given in the figure 1? So if you see here, the coordinate system is given here itself. So the flow is happening in z direction, y direction. The triangular plane is in yz plane. So the flow is happening in x direction. So I hope that will be enough for you to solve the answer. You only have to first thing to find that equation, which coordinate equation you want to, in which coordinate direction you want to find. It is easy to check the coordinate of pressure gradient. So the flow is happening in x direction, so it should be either of these three. This one be right. Again, you can find which among the following will be true. You can inbox your answers. Okay, the numbers inside the duct represents, it is kind of already discretized the zones. So the larger rectangular duct is being discretized, or what, they subdivided into 16 smaller triangles for creating what, discretizing the domain, computational domain. So the numbers are saying, so if you have watched the video, you would have understood. So each of the triangles are numbered, the subdomains. So here you don't have to concentrate on the numbers. You just have to find which equation is the one we should solve uh, in this solve for a steady laminar flow through the rectangle duct given here. So the major clue from the image is the coordinate system, that is the flow is the triangular section is in YZ plane. That's a major thing. Then if it's y in the major plane, then which is the x component of velocity? If it is happening in x direction, then the dominating velocity will be x direction, x component of velocity. So here, then again we can find here x component of velocity is u. U, v, and w are the components of velocity, and x component of velocity is u. From here itself, in option B, it is described as w, so it is again wrong. So we can eliminate two of them, and remaining two is C and D. Again, it is happening in I said YZ plane, so it can be this term can be dou u by dou x term won't be exist there. So the other one, that is the third one, flow is happening in x direction, so it will be a function of y and z. So mu into dou square u by dou y square plus dou square u by dou z square. That's the third option. Option C will be your answer. So this is the uh, momentum equation expression here. Or since it is said that steady flow, this term will cancel out. Again, other dou u by dou x and v and w, all these terms will cancel out. Again, body force equation won't be there. And again, dou square u by, since dou u by dou x is not there, dou square u by dou x also will cancel out. And remaining terms will be dou p by dou x minus dou p by dou x plus mu times dou square u by dou y square plus dou square u by dou z square. That's our answer. Solution is that's our answer, option C. Okay, next question. For a steady, fully developed flow through a duct shown in figure, that is the same triangular duct, represents a balance between which of the following terms? 1. Inertial forces. 2. Viscous forces. 3. Pressure forces. Options are option A 1 and 2, that is between inertial force and viscous forces. Option B, that is 2 and 3, between viscous forces and pressure forces. Option C, that is between inertial forces and pressure forces. Option D, all the three forces. You can inbox your answers. So if you check the terms that remained in the governing equation after cancelling all the unnecessary or all the other terms, will give the answer. So we only have to find which forces existed after eliminating the irrelevant terms in one-dimensional momentum equation and x-directional momentum equation. So this is the equation. Here this term is called inertial forces. This term we can easily understand because P is also present there. So it is pressure force. This term you can see gravity is present, that external influence of some field is there. So the external fields are affected on the entire body. Hence it is known as body force. So this term is the viscous term. Since the mu is attached to here, simply you can go viscous force. So in the governing equation, what we have seen is like we will eliminate entire left side and body force. So the remaining things are pressure force and viscous force. So that is here 3 and 2, 2 and 3, viscous force and pressure force. So answer is option B. The in the governing equation regarding that given triangular duct, the balance is between pressure force and viscous force because all other terms will be eliminated. While next question, the vector form of the governing equation for the flow through the ellipsoidal duct shown in figure 2. So here you can see there's a ellipsoidal duct. Here you can see an ellipsoidal duct. So the question is, what is the vector form of the governing equation for the flow through ellipsoidal duct shown in figure 2? Options are option A, mu del dot del u is equal to minus dp by dx. Option B, mu times del dot del v is equal to minus dp by dy. Option C, mu times del dot del w is equal to minus dp by dz. Option D, mu del square u is equal to minus del p, where u is the velocity vector. So the question is, which among the following represent the vector form of the governing equation for the flow through ellipsoidal duct? You can inbox your answers. Please inbox your answers. It's a simple, straightforward question. Um, the solution is answer D. By simply itself, you can figure it out because all other terms were dp by dx. Only for the fourth one was del p. So this is how it is. In continuation in vector form will be del dot u is equal to 0. In momentum equation, it is rho times dou u by dou t plus u dot del times u is equal to minus del p plus rho g plus mu times del dot del u. So for steady incompressible flow, the left side terms vanish. The only remaining terms are minus del p plus mu del dot del u. So if you take uh, minus del p to the other side, it will become positive del p. So our answer is D, option D. So which method would you use to solve the velocity field in the ellipsoidal duct if you wish to solve in xy coordinate system? Options are options are finite volume method, option 2 finite difference method, option C finite element method. Options are only 1, option B only 2, option C 1 and 2, option D 2 and 3. Oh, the answer is already here, but still you can think. Uh, so ellipsoidal duct is not non-conformal. It is not having a regular shape. I mean, not exactly matching with the rectangle coordinate system. So if we want to solve it in xy coordinate system, which of the following we will select? So the infinite volume method, uh, we are subdividing the computational number, the large domain, into control volumes, small control volumes, and we are integrating over the control volumes to get the solution. These integrated equations are then converted to algebraic equations. And in finite difference element, the finite difference method itself is developed from Cartesian coordinate system. So conforming with the Cartesian coordinate system is best suited for finite difference method. So the best methods for ellipsoidal duct will be either finite volume or finite element method. Which of the discretization method is known for its strict conservation properties, making it ideal for fluid flow problems? Options are finite difference method, option B finite element method, option C finite volume method, option D all of the above. Here also you can see the answer. It's finite volume method, and by formulation itself, finite volume method is having the conservative property. So because we are finding our, we will be applying our conservation law over a single element. Maybe suppose this is our small control volume in the larger domain. So we will be applying our differential equation or uh, our governing equation over this control volume, and we will be integrating over the domain. So by integrating itself gives the conservation property to it. So finite volume method by definition has conservative property. But whereas in finite difference method or finite element method, we have to uh, add other methods. We have to sometimes we have to do some more tedious works to make it conservative. So it is not by definition conservative. It is mostly in finite difference. You have seen, but we are taking that particular cell. If we are taking one particular element, these elements, if we are taking this node point, we are taking, then we will only be working with that particular element distance between the nodes, and we will be discretizing the governing equation at each nodes. But there is nowhere talking about the integration that we have to submit together. But finite volume method itself, if you can go through either Weirstick, Manalasekara textbook or Patankar textbook, uh, that is given in your reference. Those books talks extensively on finite volume method. So in finite volume method, by definition itself, we are integrating it to get the algebraic equation. So by integration itself, it is giving the conservation property to that particular method. Next question. What is the main advantage of forward and backward difference schemes compared to the central difference scheme? So this question is on discretization method, discretization schemes. So what is the main advantage of forward and backward difference schemes compared to central difference scheme? Option A, high accuracy for all derivative approximations. Option B, simpler implementation on non-simpler uniform grids. Option C, better stability for certain types of equation. Option D, ability to handle complex boundary conditions. You can inbox your answers. Okay, you have two questions here. I didn't see that. What is the difference between finite volume and finite element? Uh, so um, it's like in finite volume method, if there is a larger subdomain, larger domain is like, so suppose this is our larger domain, and we have subdivided into smaller domains. And this domain, what we have to do is like we will be applying the our equation, governing equation, that is like what we have seen in the first question, mu times dou square u by dou y square, all those equation will be applying here. Then it will be integrated over that particular governing equation, will be integrated over this control volume dv. This is the small control volume. So integration from, suppose this has a limit and this is the lower limit and this is the higher limit, it will be integrated over the entire place. Then with that equation, we will be creating our algebraic equation. So this is uh, it is kind of an integral method, finite volume method. Whereas finite element method is kind of, that is primarily developed for structural mechanics. So in uh, there, what we will be doing is like we will be creating Ax is equal to B kind of matrix, where will be a stiffness matrix, degrees of freedom, all those kind of things will be there. And the Finite element method as such is uh, suitable for structural mechanics like bending of beam, breaking of beam, that kind of thing, finite element analysis. So mostly more relevant in case of uh, solid mechanics, whereas finite volume methods are best for CFD or computational fluid methods. But there is a workaround. We can use finite element methods for solving CFD problems, but I don't think we can use finite volume methods to work on structural mechanics. So that is a different difference between finite element and finite volume. And second question was where we apply this scheme in ANSYS software. No, ANSYS software as such doesn't have these schemes. If you would take Fluent, which is a subpart of ANSYS, that uses in ANSYS. ANSYS are software packages. So in ANSYS, in Fluent, if you take Fluent, it extensively uses finite volume method. Whereas if you take structural, it is entirely finite element method. ANSYS structural. ANSYS structural, LS Dyna, all those other things regarding working with uh, what solid mechanics in that particular software. All those things are in finite element, whereas Fluent, CFX, all those things are using finite volume method. So you can't select these methods as such, because this should be this finite volume method and finite element method. All these things are considered while writing the code itself. So if you are writing a code by your own, that you can uh, uh, then you can choose which method to follow. So inside answers, you can't switch in between. Okay, hope that answers your question. Next, how we come to know that ANSYS software is using either FDM or FVM. They have clearly, mostly they have, I told you, it's like if you are using Fluent, that is in CFD domain, the main solver they have is Fluent. So ANSYS software is like ANSYS the entire package, I think you are mentioning, in, or ANSYS Workbench may be. But if you are taking Fluent, if you go to their website, they are and in their product information itself, they'll be giving what kind of methods they are using. And Fluent extensively uses finite volume method. Finite difference method as such we are not using anywhere. Finite difference method is kind of starting point. You can say as a starting point of both finite volume method and finite element method. Its advanced versions are the advanced versions of finite domain and finite element uh, is what we are using now. I hope that answers the questions, Kamal Costa. Okay, so please answer the question. Answer the sixth question. What is the main advantage of forward and backward difference schemes compared to central difference scheme? The schemes we have discussed in last class also. I mean last interaction section also. How to write to answer the question. Even if it's wrong, it's fine. Yes, the answer is simple implementation in non-uniform grids. Option B. So let me explain to those who didn't get it. In forward or backward, this is forward equation. This is the backward equation. In forward equation, uh, the information of f of xi is generated. F of I plus 1 is generated from only one direction, that is I plus 1 minus xi. So in the information is taken from only right hand side of the element, whereas in backward equation it is only taken from the left hand side of the equation. So we only need the data from either one of the sides. So that makes uh, backward or forward equations more useful in application of non tonal meshes, because in while implementing boundary conditions and all, we won't be having both sides. But if you see in um, central difference equation, you will be needing data from both sides. So our answer is option B, that uh, for non-uniform grids, uh, either backward or forward schemes will be better than central difference methods. Next question. What is the primary factor to consider when choosing meshing strategy for a CFD problem? I hope this question can be answered by all. Option A, cost of the meshing software. Option B, users' experience with the meshing tool. Option D, balance between accuracy, computational cost, and meshing effort. Option D, availability of predefined mesh templates. That's kind of a straight practical question or applicative question. Try to answer. Okay, this is a question. How many number of mesh elements are sufficient to get better accuracy? Uh, um, that question itself have a lot of questions. Yeah, we will discuss towards the end of our this today itself. We will be discussing on that. Uh, Simple answer is like it will entirely depend on your computational geometry, which is the computational domain. What is the shape of it, and uh, how complicated it is. And there is a method to find that number of elements. We'll discuss on that. Okay, here our answer is uh, option C. That is balance between accuracy, computational cost, and meshing effort. So this meshing, that is discretizing and meshing is two different things. Discretization is about the equation and subdividing our governing equation, whereas meshing is dividing the geometrical domain. So suppose we have a domain, so then how we are dividing it. This is what uh, meshing is. So I don't know how many of you know there is a dedicated meshing softwares for that, and also it is without even getting into CFD, finite element, anything. That meshing process itself is a tedious process. We are if you are using any software like ANSYS or some console or something, you are taking it for granted, but the meshing process itself is tedious. If you are writing a code to mesh or subdivide a geometrical domain, you will understand how much difficult that it is. And this doesn't matter. This also doesn't matter. So our answer is option C. Next question. Which of the following factors primarily influences the accuracy of a CFD simulation result? Options are option A, geometry complexity, option B, mesh type, option C, mesh density, option D, software used for meshing. I think now you know why I didn't answer the question. You can try to answer this question. Which of the following factors will primarily influence the accuracy of CFD simulation result? So if you find uh, more than one options will influence the accuracy, then find which among the following will have the uh, maximum influence on the CFD simulation result. In this question, you will find more than one question suitable, but the most important among the following is mesh density. So mesh density is like how dense, or it's like uh, as you said, if you are taking, we are taking some particular volume, how much uh, numbers of nodes or meshes there present in that particular region. That is mesh density. So the mesh density matters more than structured or unstructured, because structured and unstructured is the type, uh, and geometrical complexity, everything. Uh, the thing is like mesh density. Like we may have to suppose we have a complicated geometry. In some regions, we will be needing for a high denser mesh. In other regions, we can go for a lower mesh. I mean, uh, less denser mesh. So if you have seen some meshes, then when suppose floor a wing, some floor in NACA profile or something, then you will see where the flow hitting that particular foil, that particular object, in that portion, the what the density of the mesh will be very much higher. But moving away from our region of interest, because suppose this is the flow domain and we want to study the flow over a this profile, NACA profile or something, some aerofoil. So flow is coming from this region. So this is the region of interest. Our the immediate surrounding of this particular body is our region of interest, and flow past this body. So this region, this particular region will be having of high interest, and obviously that region will be having higher mesh density because we want to capture everything happening there. But when we go away from this region of interest, we can have lower or less denser meshes because we are not interested in what is happening there, but we need that region for the application of boundary layers, boundary conditions, and to create the entire flow domain we need that. And the boundary conditions will be applied on boundaries, and from boundaries that boundary condition will be transported or what mm, connected to our region of interest by these less denser meshes, and the region of interest will be having high density meshes. Hope that clears it. Next question: when comparing a structured and unstructured mesh with same number of elements for simple geometry, which one is likely to have better solution accuracy? Option A, structured mesh. Option B, unstructured mesh. Option C, both will have same accuracy. Option D, depends on the specific flow problem. So the question is on comparing structured and unstructured mesh. Which one among will be having better solution accuracy given that it has same number of elements? If the answer is structured mesh, while both of these meshes can give good accuracy, the structured mesh with same element count typically gives better control over the element quality and alignment, leading to potential higher accuracy and for simple geometry. But the thing is like the question is kind of uh, little misleading. So it is only become option A because not only we have mentioned same number of elements and for a simple geometry, this is the catch here. So if the geometry is not simple, then obviously it will be unstructured mesh. Yes, only because we have specifically mentioned for a simple geometry, then only the structured mesh will have better solution accuracy compared to that of unstructured mesh. Uh, Suppose it is a complicated geometry with a constraint of same number of elements, then structured mesh won't give you a better result. So this entire question depends on what type of geometry. So this is the main thing, and this is treat this as a constraint. Now same number of elements. Next question: how are boundary conditions implemented in CFD methods? So how everybody knows what is boundary conditions. The question is how it is implemented in CFD methods. Option A: they are applied directly at grid points, as such in finite difference method, or in element nodes, as such in finite element method. Option B: source terms are incorporated into the discretized equations. Option C: both A and B are used depending on the specific boundary condition. Option D: it depends on the specific solver algorithm used. The question is on the implementation of boundary conditions. Okay, the answer is option C. Uh, so the boundary condition can be applied either on directly on the grid points. It is called uh, explicit boundary condition. So we are mentioning it explicitly, and also we can incorporate it through source terms. It is called implicit. So we can introduce boundary condition either explicitly or implicitly, depending on the particular problem or condition we have. Next question: which of these best define Dirichlet boundary conditions for the property phi at a point B in the boundary? So the question is for Dirichlet boundary condition. So how a Dirichlet boundary condition for the property phi is defined at the boundary B? Options are: option A, dou cube phi by dou x cube; option B, dou square phi by dou x square; option C, dou phi by dou x; option D, phi at B. You can inbox your answers. answer is option D, that is phi at B. So there are three different types of boundary conditions. That is Dirichlet, Newman, and Robin. These are three simple types of boundary condition. This Dirichlet boundary condition is similar to the explicit implementation of boundary condition. That is, we are uh, defining, we are giving, suppose we have a computation domain like this. Here it is A, B boundaries are A to B. Then here we can apply as phi of I is equal to phi B. So like uh, TB is equal to phi is the context is like transporter property here. So if it is temperature, if we are taking it as temperature, then temperature at B is equal to 100 degree. That suppose we are maintaining this edge of the compression domain at 100 degrees, then we will be equalizing that to that property, transporter property. So temperature at B or phi at B is equal to 100 degrees C. So that is the implementation of Dirichlet boundary condition. So here phi and subscript B gives phi at B. So that is the simple representation of Dirichlet boundary condition. Whereas Neumann boundary condition is we are giving a gradient of the property. We will be directly giving the gradient of our transporter property. Suppose phi is the transporter property, then gradient is dou phi by dou x. So this type of boundary conditions are called Neumann boundary condition, and it is used for uh, our insulated boundary conditions and all. Insulated boundary conditions cooling, all such where there is a variation with respect to x direction or in the direction of transportation. If there is a variation, then such kind of boundary conditions are implied. So there is Dirichlet boundary condition, Neumann, and Robin. Simply we can say it's a combination of Dirichlet and Neumann boundary condition. Next question: what is the main advantage of finite difference method compared to finite volume method and finite element method? So the question is on comparison between three schemes, which is the main disadvantage of finite difference method. Option A, higher computational cost. Option B, less complexity for computational complex geometries. Option C, difficulty handling unstructured measures. Option D, all of the above. So you have to find which among the following is the main disadvantage of FDM compared to FVM and FEM. There is a question why it is FDM is high computational cost. As such, you can't say that FDM is having higher computational cost, and it depends on the geometry. But here the question is uh, uh, what comparison between finite volume method and finite element method. So in finite difference method, for uh, in comparison, if you are comparing for a complex geometry, then uh, suppose we have some irregular geometry, then while meshing, what we have to do is making to make uh, what finite difference method, we want structural meshes. So uh, to get a structural mesh for this particular domain itself is having difficulty, and again we have to find normals in all the direction. This uh, if you have gone through the triangle duct lecture, then you will find that we will be finding all the normals and all. So all these things are needed here. So when the geometry becomes complicated, finding normals, meshing, all those things becomes added effort. So that is why FTM uh, is having a higher computational cost when compared to finite volume and finite element method. So if you go for very simple geometries, uh, then finite, because simple geometry, like you only need to study some uh, uh, but lid driven cavity problem or something, then the best method will be finite difference method, because the 2D problem, also uh, rectangular domain or square domain, then it will be the least computational cost method. But for everything else than that, the computational cost will be higher. So here our answer is option D, all of the above. Next question is on here onwards. The questions are on quality metrics of the mesh. The question is, the ratio between longest side and the shortest side of the mesh is called. If we are uh, considering a single element or volume of that mesh, then what is the ratio between longest side and the shortest side is called? Option A, mesh orthogonality. Option B, mesh skewness. Option C, mesh aspect ratio. Option D, mesh smoothness. So, in order to have a good mesh, there is some mesh metrics, mesh quality metrics are there. All these mesh orthogonality, skewness, aspect ratio, smoothness, all these factors are there in quality metrics. But here the question is on what is the name for the ratio between longest side and shortest side of an element or mesh. That's the question. How much aspect ratio we need to maintain? And then again, it depends on the particular problem. Uh, what kind of geometry you have. It will depend upon the aspect ratio of that particular uh, geometry type of cells you are creating. There are different types of elements or cells. Uh, there are, if it is 2D, you can have triangular cells like you have seen in the second week video, or you can have rectangular video, or you can have quadrilateral elements, hexahedral, in going to 3D, tetrahedral, quadrilateral, hexahedral, pentahedral, or polyhedral. All those elements are there. So it entirely depends on the type of element you are choosing. The answer is option C, that is mesh aspect ratio. So if you take here, it's a simple representation. So for a 2D mesh, it is like delta x by delta y. That's the ratio between longest side and shortest side. But if you see here, uh, this is a 3D element. In 3D element, it becomes the aspect ratio is defined as a by b. Like a is the uh, half of the diagonal, or the distance from centroid to the vertex, the longest or far away vertex, divided by b is the uh, distance from centroid to the face centroid. So this becomes aspect ratio. So uh, if you are taking tri or tetrahedral elements, then the aspect ratios will be in these terms, that is half of r by r, where small r is the inscribed radius or in radius, and capital R is the uh, circumradius. Again, if you come to quadrilateral elements, then it will be a ratio of minimum and maximum diagonals. So this is a quadrilateral. So a by b, that is minimum among the the maximum length of the diagonal divided by minimum length of the diagonal. Again, if you are coming to three-dimensional cells, that is hexahedral cells, then again it will be minimum edge length by maximum edge length. So again, it can vary for this only for hexahedral. Then there is polyhedral uh, type of elements are there. So all these, when you moving from when you are choosing the element type or mesh type, there itself the quality differs. So there you'll be hearing from some websites or some random blog post like aspect ratio 0.3 or something like that. If you are using answers, do this. If you are using that software, do that, something like that. But if you want to do as the as scientifically as possible, it entirely, my answer is, it will entirely depend on the type of element you are choosing. So if you are choosing hexagonal element, then it will be having some ranges. So first, when you are choosing polyhedral element, if you want to um, study a flow through a tube kind of thing, just example. So and you are using hexahedral elements, so it will be different. The best element to study the flow inside a circular bodies or something is like polyhedral. It's like pentagonal or octagonal shapes, like the particles you may have seen from the thermocouple. So that kind of elements will be the best suited. It will be having the mm, area to volume ratio, best area to volume ratio. So there you can you have to check which aspect ratio you have to follow. So you will be choosing one particular kind of element for the visual aspect, and you will be giving some random aspect ratio values. You will be limiting yourself to some aspect ratio values. So don't get confused between some particular ranges of aspect ratio discussed in some blogs or website. First, understand that the aspect ratio is an entirely geometrical property, and that geometrical property is uh, always chosen in accordance with the type of elements in the mesh. And also, again, if uh, when you are using ANSYS or some other software packages, you have to check how they are finding the aspect ratio. They may not be using this kind of equation, they will be using some other kind of equation which is computationally uh, easier for them. So that also you have to check. So if you are making in entirely mesh by yourself, suppose in MATLAB or some Salom or something, you are creating your own mesh from scratch, then you will know how this aspect ratio and everything is varied according to your uh, input. Hope that answers the question. Moving on to next question. How does high aspect ratio affect the accuracy of CFD simulations? So the question is, what is the impact of high aspect ratio in the accuracy of CFD simulation? Options are: it improves solution stability in turbulent flows. Option B, it reduces numerical diffusion in all flow regimes. Option C, it leads to interpolation errors and poor resolution of gradients. Option D, it has no impact on solution accuracy. So this answer, inbox your answers. What is the impact of high aspect ratio in in the accuracy of CFD simulations? Let me take a 2-minute break. I'll be back in a minute. Please inbox your answers. Yes, the answer is option C. It leads to it leads to interpolation errors and poor resolution of gradients. So this high aspect ratio cells, that is called elongated element, it is also called spaghetti elements, spaghetti cells. So elongated elements. So these spaghetti cells or high aspect ratio cells can cause errors in the gradient calculation because you can see this. If we take one element like this, that uh, we are connected to other elements through this direction. The gradient in this direction, that is x direction, will be uh, will have to calculate it with larger distance. That dx here will be much larger than the dy. That is, I am saying the uh, distance to the other centroid or other element will be much larger. So that's why the gradient, this calculation of gradient in dx direction, x direction will, because dx, this element, the length itself is high. So such uh, a large values of dx or some that directional large values can create uh, poor resolution of the gradients. Moving on to next question. What is the meaning of skewness in the context of mesh quality? So the question is on the next metric. What is the meaning of mesh skewness? Option A, presence of duplicate elements in the mesh. Option B, non-orthogonality of element faces. Option C, unequal aspect ratio of elements. Option D, distortion of element shape from ideal geometries. So, what is the meaning of skewness? That is another word you might have heard in the context of mesh quality. So, what is the meaning of skewness? You can inbox your answers. Yes, our answer is option D, distortion of element shape from ideal geometries. So, for a 2D element, it's like the ideal shape is like equilateral triangle. So this is a highly skewed triangle, and you know what is a equilateral triangle. So the all sides must be equal, and the included angle must be 60. All those constraints will be there, but uh, this is the ideal case for a triangular element, and for uh, rectangular element, it's an equiangular chord, which is an ideal element. So that is, all the angle should be 90 degree. So this is the ideal case, and this is a skewed case. So again, uh, this skewness, this variation from the skewness can create that aspect, like aspect ratio itself. The skewness, if you have checked the our second week's classes, you might know what uh, that how the triangular shapes normals are have been calculated. We will be using cos and trigonometry functions in finding normals and all. So with variations in angles like zeros and ones, higher angles can create issue while calculation. So that's why we need some particular, because for finding normals and all, we need angles. So when it gets this angle gets skewed or very high values of angles are present in there, then the calculation gets unrealistic, gives unrealistic answers. So again, there are different metrics to find skewness. This is one type for triangle. You can see this two diagonals. I mean, one from the vertex and to the face center of the opposite uh, side. This is between two face centers. So the angle between these two lines is taken as skewness angle. That's 1 minus maximum of 90 degree minus alpha 1. That alpha 1 is this included angle. Likewise, for chord element, this is the skewness angle measurement. And again, if you check across the softwares, there will be difference in skewness angle calculation. So they will be having their own ranges of skewness angles and all. So again, my point is to check what kind of elements you are using. Then only go for some hard uh, values, ranges of values, rather than trying to find one particular value for your computation. Next question: what does orthogonality measure in a CFD mesh? So another mesh quality metric is called mesh orthogonality. So what does this orthogonality measures? Option A: alignment of cell faces with the flow direction. Option B: deviation of cell face normal from the ideal direction. Option C: smoothness of cell size transition. Option D: the ratio of longest to shorter edge of the cell. So the question is, what do you mean by mesh orthogonality? You can inbox your answers. Our answer is option B, the deviation of cell face normal from the ideal direction. So suppose these are two cells, cell 1 and cell 2, and this is the this blue arrow line is the boundary of two cells, the boundary shared by two cells, and then this black lines connecting these two dots, that is the centroid of each cell, is the um, face normal, and not face normal, the line connecting uh, cell centers, adjacent cell centers. Then the normal cell, uh, this red arrow indicates the there is a vector perpendicular to the cell face of cell 1. So this is the vector or normal, a cell face normal, and it is that the variation from variation of this normal from the line connecting the cell centers is called orthogonality or non-orthogonality. So for it to be orthogonal, it should align with each other. That is orthogonality. And some softwares, if you check, it will be given not orthogonality mesh. It won't be saying mesh orthogonality. It will be saying mesh non-orthogonality. So that is the angle created here. How much it is having a particular angle. So this will again this normals made sorry this angles made by the normals will again come into picture while uh, computing the flow properties. Next question: why is non-orthogonality is a concern in CFD simulations? So the question is, what is the impact of non-orthogonality in CFD simulations? Option A: it increases the stability of numerical schemes. Option B: it enhances boundary layer resolution. Option C: it introduces interpolation errors and reduces solution accuracy. Option D: it has no significant impact on simulation results. You can inbox your answers. So again, answer is option C. It introduces interpolation errors and reduces solution accuracy. Like we have discussed earlier, uh, this non-orthogonality will also uh, impact on the calculation of gradients. So the gradient calculation will be impacted by the presence of non-orthogonality. So our aim is to reduce this non-orthogonality as much as possible. Next question: which mesh quality metric is most crucial for maintaining smooth transition in cell size across computational domain? So the question is on which of the which quality metrics among the following is most crucial for maintaining a smooth transition in cell size across computational domain. Options are: option A skewness, option B growth rate, option C orthogonality, option D aspect ratio. You can inbox your answers. Yes, the answer is option B, growth rate. Growth rate is also known as smoothness, mesh smoothness. So how the transition, because the density variation, suppose you have a dense mesh and a coarse mesh, or less denser mesh in the same domain, computational domain, then how, uh, suppose this is the dense mesh or fine mesh, and this is the coarse mesh, both in same computational domain, then how it is uh, growing from one to other. I mean, from how the transition from finer to coarser is happening. So that is called smoothness or uh, growth rate. So it needs to have some particular value. Like someone has told this 1.2 or something. So it has to maintain some particular uh, transition, I mean, gradual transition should be there to capture the gradient. Suppose if you see here, the transition, like all these three layers is having one particular height. That's delta y is kind of similar in all these four layers. But suddenly there is a jump from here to here. So what will happen there is like some of the parameters calculated, some of the flow properties calculated won't give good results, or some errors can creep in if we are giving some this kind of uh, uh, abrupt jump. So the best method is to give some uniform growth rate. So if you see here, this is one, the another layer is slightly bigger than the precedent layer. So like it is kind of growing from one portion to another, and the mesh density. So such kind of smooth transition from fine mesh to coarse mesh should be defined. So it is called growth rate or smoothness. Next question: what is the primary impact of poor mesh smoothness in CFD results? We have already discussed. Options are increased computational time, but no effect on accuracy. Option B, artificial oscillations and convergence issues. Option C, reduced boundary layer resolution. Option D, increased accuracy due to refined mesh transitions. So which among the following is primary impact, good or bad, in the CFD result? Answer is option B, artificial oscillations and convergence issues. So there's a question, what is artificial oscillation? Artificial oscillation is simply a numerical instability actually. So suppose uh, we have one value, uh, this is the number of iterations or something, this is value of u or something, you can take velocity or something, any one parameter. So due to this kind of uh, uh, non-smooth grids, what will happen is like, suppose in first iteration or some uh, nth iteration, it will be having some value here, and next iteration it might be giving the same value, it will be in by calculating it will be giving somewhere here, and it can go like this, it can converge or diverge. So it's like it will be like oscillates. So somewhere actual value will be somewhere here, but it won't converge to that. Our idea is to this value should be converged to that value of u uh, by but carrying out reasonable number of iterations. But uh, due to this lack of smoothness between the mesh layers, it will oscillate what maybe to and fro of the actual value, or beyond the range of the actual value also. It can just keep on oscillating. It won't it's not like that. It won't ever converge or something. It can create serious convergence issues because these values will keep on oscillating rather than to converge to a value. So that's what's called on artificial oscillations. Oscillation. That's why I have drawn a diagram here. It the values will be uh, actually it should give somewhere here in second. So but it will under predict, and in another in the next iteration it will over predict, and this series of over predicting and under predicting cycles will create oscillation kind of movement in the results. So that is called artificial oscillation, or it's kind of a numerical instability, it won't get stable. So that's what it's called, artificial oscillation. Hope that clears it out. The next question, which type of mesh is best suited for complex geometry with curved surfaces? Options are structured mesh, option B unstructured mesh, option C hybrid mesh, option D all of the above. So the question is on applicative level. Which type of mesh is best suited for complex geometry with curved surfaces? The catch here is curved surface. Which type of mesh is best suited for complex geometries with curved surface? It's not only just complex geometry, the complex geometries having curved surface. Our answer is option B, unstructured mesh. So, because unstructured mesh will give a greater flexibility to attaching to the complex shape or curved shape in the complex bodies. Simply, structured mesh is kind of, uh, if you have any doubt between structured and unstructured mesh, structured meshes are those mesh that can be those meshes that can be what fitted or written in accordance to Cartesian coordinates. Like this, if you can see, this is a Cartesian mesh. Here, everything you can write in terms of x and y. There, this is kind of curvilinear mesh. There is mostly having like what uh, Cartesian mesh, but in some points where the curve is there, uh, it is kind of made most little finer with a inclination. So those kind of meshes are called curvilinear meshes, and it's like it will be still Cartesian meshes, but the Cartesian xy direction. I mean, this kind of conformality will be in another plane. That's only difference. So this is a curvilinear body fitted mesh. This inside is a NACA profile. So if you can see, this is again a Cartesian mesh, but it is fitted uh, in accordance to conform with the curved body. So it's a curvilinear structured mesh, but for a complex geometry, this creating a structured mesh will be difficult. So best suited will be unstructured mesh. So unstructured mesh, you can see this is also I mean chord elements, but it is not like rectangular mesh. It's quadrilateral mesh. So these are example for unstructured meshes. This is triangular or tetrahedral meshes. So triangular is for 2D. The same variant when it is in 3D is called tetrahedral meshes. And polygon that I have discussed earlier. This is the polyhedral mesh. So it will be like uh, the simplest example is like if you have cut open a thermocol piece or something, you will find these kind of grains there. So that is polyhedral. So all these are unstructured meshes. Whereas hybrid meshes is the coexistence of both unstructured and structured mesh. So I saw some few people has answered hybrid mesh, but creating hybrid mesh uh, everywhere will be cost consuming and time consuming. So these kind of hybrid meshes are only given where we need. Uh, if you see here, you can see this is a tetrahedral mesh. This is a flow around wing, NACA profile kind of scenario. Here it is the wing is meshed with tetrahedral meshes, and also the flow region is also meshed with tet mesh. But if you see the boundary layer, that flow where the flow is hitting the solid, that region is what created with structured mesh. So here both structured and unstructured mesh exist. Here hybrid polyhedral. You can see the wing and the floor domain both are created with polyhedral meshes, but this the boundary layer region is of our region of interest. So it is meshed entirely with structured mesh. So these kind of meshes are called where structured and unstructured mesh coexist. These such scenarios are called hybrid meshes. So best and efficient method is unstructured grid because hybrid meshes are only for specific purposes since it is cost consuming. Next question. What is the key difference between explicit and implicit boundary conditions in CFD simulations? Option A. Explicit conditions specify value directly at the boundary. Option B. Implicit conditions involve solving additional equations at the boundary. Option C, explicit conditions are more accurate while implicits are faster. Option D, explicit conditions require special machine near boundary. What is the key difference? Which among the following is the important difference between explicit and implicit boundary conditions in CFD simulations? You can inbox the answers. What is the key difference or important difference among the following when comparing explicit and implicit boundary conditions in CFD simulations? These two we have already discussed that explicit condition is like specifying values directly at the boundary, and implicit is like we will have to add as a source term. The boundary condition will be added as a source term in the equation. So option B is kind of saying, telling the same. Implicit condition involve solving additional equations. Or sometimes when we are adding the source term in the equation, we may have to add more equations to close the problem. So there are such instances we'll be seeing in our lectures, coming week lectures. Like somewhere, some places there are when we are introduced boundary condition as source term, then that source term itself will have we have to solve another equation for that source term to close the problem. So which among the following is the important difference? Okay, our answer is option C. Explicit conditions are more accurate while implicit are faster. So if we are establishing explicit boundary conditions as explicit, then we will get more accurate solution. But if we are giving this boundary conditions as implicit, then simulations will run faster. So it's like we have to choose between mm, how to implement the boundary condition, whether we have to give it directly or we have to give us the equation or source term or something that we have to find by determining what we need. Accurate, we need a more accurate solution or faster solution. So that's the solution. So that's all for today. We can meet next week. Thank you for joining.